Okay, let's just dive right into the fascinating and completely invisible universe of waves that are literally transporting energy all around us right at this exact second. Welcome to this explainer. We often picture the universe as being made mostly of solid objects, right? But the reality is actually shaped by this constant, chaotic, yet beautifully structured storm of waves moving with extreme microscopic detail. Today, we're going to unpack exactly how that works. To help us navigate all this, here is a quick roadmap for today. We'll be covering 1. The invisible waves around us, 2. The anatomy of a wave, 3. The electromagnetic spectrum, 4. Everyday invisible waves, and finally, 5. High energy, high danger. All right, let's kick things off with Section 1, the invisible waves around us, specifically comparing mechanical and electromagnetic waves. So there's this fundamental rule of physics that basically divides absolutely all waves in our known universe into two massive categories. First up, mechanical waves. These guys absolutely require a physical medium to travel. Think air or water. They transport energy by literally bumping adjacent atoms into one another in this crazy cascading chain reaction. But then you have electromagnetic waves. These are the ultimate rule breakers. Because they're self-propagating, oscillating magnetic and electric fields, they don't need a medium at all. They can travel completely freely right through the total vacuum of space. How wild is that? To really ground this in reality, let's look at a pretty terrifying example of a mechanical wave: massive seismic waves. These are born from extreme tectonic strain that releases kinetic energy during intense geological events, like volcanic eruptions or sudden rock shifts. When an earthquake hits, primary waves, the P waves, arrive first, quickly followed by secondary waves. They transfer immense energy directly through the dense rock itself, literally shaking the ground beneath our feet. Moving right along to Section 2, anatomy of a wave and how particles actually move. Now, what's really fascinating is what happens when we zoom way, way in to look at the extreme detail of how these particles actually move as energy passes through them. The absolutely crucial point here is the architecture of the movement. Basically, there are two primary types of vibrations. First, we have transverse waves. Here, the particles vibrate up and down at exact 90-degree angles. They're completely perpendicular to the wave's direction of travel, which gives us those familiar crests and troughs. Second, we've got longitudinal waves. With these, the vibration of the particles is parallel. They're displacing back and forth along the exact same axis as the wave's path. If we look at those longitudinal waves with some granular precision, we can actually see that they operate through alternating pressure zones. So as particles shift back and forth, they bunch up to create compressions. These are the localized areas of the highest density and pressure. And then they violently spread apart into what we call rarefactions, the areas of lowest density and pressure. It's exactly this continuous, rhythmic squeezing and stretching that forcefully pushes the energy forward. All right, on to Section 3, the electromagnetic spectrum and how these forces travel through space. Let's see how all this builds into those invisible forces we mentioned that don't need a physical medium at all. See, while mechanical waves, like sound or water, are relatively sluggish because they rely on bumping heavy physical particles around, electromagnetic waves are completely untethered. Because they travel through a vacuum without any physical resistance, they propagate at the mind-boggling speed of 3 × 10 to the 8th power meters per second. Yeah, that is the literal speed of light. This entire electromagnetic spectrum maps out the range of wavelengths for all known EM waves. And as you'll see, different energy sources produce distinctly different wavelengths. On one end, you have the drawn-out, kind of lazy peaks and valleys of low-frequency radio waves. But as you move across the spectrum, the waves compress. They pack tighter and tighter together, ultimately culminating in the extreme, ultra-high frequency and highly energetic gamma rays on the far end. Which brings us to Section 4, everyday invisible waves, and how they power our modern life. We are constantly harnessing the lower frequencies of this exact spectrum to power our daily lives. I mean, it's pretty amazing. By tuning receivers to specific frequencies, we can essentially pluck distinct signals right out of thin air. We pick up radio waves propagating from antennas for TV broadcasts, RFID chips, and even deep space astronomy. Moving slightly up the spectrum to microwaves, we use those to power our cell phones, heat up our lunch, and communicate with GPS satellites orbiting the Earth. As we ascend further up the energy spectrum, the applications really start to change. Infrared allows us to detect thermal radiation. So that powers thermal imagers, optical fibers, and even the heat radiating off an electric grill. Next up is visible light, which bounces off objects and gets captured by camera sensors or, our own eyes. Above that is ultraviolet, which actually packs enough punch to instantly sterilize water. But there is a catch. Intense visible light can chemically overload and severely damage your retina. And UV radiation causes direct cellular surface damage. That leads to sunburns and can mutate skin cells, which is a major trigger for cancer. That naturally leads into Section 5, high energy, high danger, exploring the extreme end of the spectrum. So here we are at the double-edged sword of high-frequency waves, and the absolute unbreakable rule of physics you really need to remember here is this. As the wavelengths shrink and the frequency skyrockets, these waves gain incredible and, quite frankly, sometimes dangerous penetrating power. We're talking extreme detail here. Their wavelengths become so unimaginably small that they literally stop bouncing off atomic structures and just start slipping straight through them. Believe it or not, we actually weaponize this exact penetrating power of gamma rays, which are the highest frequency waves on the spectrum, to save lives. In medicine, doctors can precisely target them to penetrate the skull and destroy brain tumors right at the cellular level for cancer treatment. In agriculture, they're used to shoot straight through the surface of fruits, like strawberries, instantly sterilizing them by irradiating and killing off harmful bacteria. We even use them to completely sterilize surgical equipment. Industrially, this extreme radiation is incredibly useful too. Because it can look right through dense, solid objects, engineers use gamma rays along with photographic film to expose internal welding flaws and microcracks that are hidden deep inside thick metal pipes. The high-energy radiation just easily pierces the metal matrix, leaving behind a neat little shadow of any structural weakness on the film behind it. But when we zoom in to the absolute microscopic level, we see the grave danger of this technology. The exact same extreme penetrating power that lets gamma rays and X-rays pass through dense metal allows ionizing radiation to pass right through soft human tissue. And when it does, the interaction at the atomic level is seriously violent. Step by step, it looks kind of like this. The ultra-high frequency wave pierces a human cell completely undetected. The radiation easily breaches the cell's inner nucleus. Then, because the energy is just so intensely concentrated, it acts as ionizing radiation. It literally knocks electrons right out of their atomic orbits. This physical disruption violently shatters the chemical bonds of your DNA strands, and this severe cellular damage can scramble your genetic code, causing very dangerous unchecked mutations. It's an incredible mechanism of physics for sure, but an absolute lethal hazard to biology. So as we wrap up this explainer, I want to leave you with a quick thought. As you sit there right now, just consider the thousands of unseen waves cascading over you, from the low-energy Wi-Fi signals connecting your devices to the high-speed cosmic rays arriving from distant stars. They are all silently passing right through your cells at this exact second, a complex, invisible storm constantly connecting us to the hidden mechanics of the universe. Just how much energy is flowing right through you, right now?